Yeah.
Like I was just thinking, like, we need to do something about this. Like, why is it even doing something so we don't have to do that?
Yeah, I know.
So, you may recall that in chapter 2, we learned a methodology for circuit analysis that had steps 1 through 6, and we would burn through those, and we would find a time response to a system with initial conditions. And, well, you may recall it because, you're still doing it in your homework. By the way, the transformer problem, special problem 2 from the homework, I'm pushing to next week because we haven't talked about transformers yet. But the first problem is problem enough, I guess. So, yeah, get going on that if you haven't yet. It's a second order differential equation with a sinusoidal input. So it's, you've got, it's some work. It's some work. Okay. So we learned that method, 6 steps, and you get the time response. And we said, oh, look, there's this sinusoidal component that just stays forever, and then there's this transient component that, so there's this sinusoidal component that we call the steady state component, and then there was the transient component, which is this decaying exponential term, right? And it gets really small after 6 time constants or whatever. And so we said, well, maybe there's a way to find the steady state response without going through this whole process and solving the differential equation. And that's what we're building up to. We introduced impedance, and now we're ready to introduce that method. So that's what we're going to get we're going to get 6 steps. They're very similar to the other 6 steps, but there are a few places where it's a little different. And we won't have to solve a differential equation. And some of you are like super relieved about that. But don't worry, you'll still get practice doing differential equation problems, like your homework this week. Okay, step 1, draw a circuit diagram. That's same, right? Step 2, label with the assumed direction of current flow each element. That's the same. Nothing's changed so far. Write generalized Ohm's law for each circuit element and define the impedance of each element. Well, now we got something new, but it's actually it's taking the place of writing the elemental equations, right? And actually, the position we're going to take is that generalized Ohm's law is the elemental equation for every element. It's just always going to be V equals IZ for whatever element it is. Say it's like capacitor 2, so it'd be VC2, IC2, ZC2. But then for every element in the circuit, you've got V equals IZ, V equals IZ, over and over again. Okay, but it's pretty much the same. It's just that instead of having elemental equation that's kind of unique to each situation, you've got the same elemental equation for everyone. Okay, step 4. For every node not connected to a voltage source, write Kirchhoff's current law. That's the same, step 4, as before. Step 5 is Kirchhoff's voltage law, KVL. So current law and voltage law, same step, same step. Step 6 is a little bit of difference here as well. So you probably have a linear system of 2n algebraic equations and 2n unknowns, where n is the number of passive elements in your system, to be solved simultaneously. I mean, that's really all we need to say. And they're all algebraic, which is nice. So you can just solve for the output, whatever it is you care about. Say the voltage across a capacitor, just solve for it algebraically in that system of equations. Now you can solve for all of your unknowns. You can solve for the voltage across every element and the current through every element, because those are all your 2n equations and unknowns. That's what they describe. Often we only care about one or two of them, though, so we don't always want to solve for everything. And in that case, you can follow these ABC steps that will, potentially, for simple systems, get you there. But in general, all we have to do in step 6 is just set up a system of equations, and we could use those linear algebra techniques. We could invert a matrix, or we could use Gaussian elimination, right? Which is much more efficient, actually, algorithmically speaking, than inverting a matrix. But the solution is within your grasp, and it's something that you guys have all learned how to do. You're probably more comfortable with than differential equations, is just my guess. I don't know for sure, but solving linear algebraic systems is it's like your bread and butter, right? I've just been eating that for years. You're really tired of new professors teaching it to you, too, I'm sure. Like, this again. Substitution, elimination. Yeah. So I'm not going to teach it to you. You're welcome. So this is, these are the steps. So first, eliminate half the unknowns by substitution into the elemental equations, which are just generalized Ohm's law equations. So that's the same step we did before. We can eliminate half of them just like off the top, which is nice. And then step B, try substitution to eliminate or to get down to only those variables of interest and inputs. So maybe you only care about the voltage across the capacitor, so you want to eliminate everything down to just the voltage across the capacitor and the input voltage. And then the last thing is to just solve the remaining system of linear algebraic equations for the unknowns of interest. So maybe you cared about two, maybe voltage across the capacitor and the current through an inductor. Then maybe you eliminated all the variables that were not that, and then you have to solve that system for the unknowns. So that's really all there is to it. It's actually scary easy, with the exception of the confusion that can arise around phasors and complex numbers and stuff. That's almost always where the confusion arises. Once again, not with the engineering analysis stuff, just with the maths. It's always the maths. It's always the problem. Okay, so let's do the same example we did in chapter 2. It was the second example we did. It was for an RL circuit with a sinusoidal current source. Remember this? We're going to solve it for the steady state current and voltage, whereas last time we solved it for just the general solution with initial conditions. This time it doesn't have initial conditions. The lack of initial conditions, the fact that I asked for the steady state current and voltage, and the fact that I explicitly said we'll use impedance methods should indicate to you that we're going to use impedance methods. Okay? So those are the three things. But any of those alone might have triggered that. The steady state and explicitly saying use impedance methods, those are the two that are the strongest ways of indicating that. Not giving an initial condition isn't maybe grounds for much confidence that we can just do the steady state solution, but in certain instances maybe you could make that assumption. Okay, so we will just start hitting on this problem with our algorithm, with our 6 steps, right? So I used to go to this church back in the day when there was a pastor who used to make fun of well-intentioned, but sometimes oversimplifying folks around like religion and stuff. And he would say things about like the 5 happy hops to heaven, stuff like that. So we have like our 6 sexy steps to success. I don't know, something like that. I just made that up. I feel like we could get a better term than that. Okay, so I did this problem last night, and then I did this problem this morning in the other section. I'm going no notes on this, and we'll see how we do, okay? All right. Last night I also went no notes because they weren't made yet, so that's what I made. So step 1 and step 2, actually, as was the case last time, drawing the circuit diagram and labeling the direction of the assumed current flow. That's already done. So we're already on step 3. And step 3 is the elemental / generalized Ohm's law, right? And we like to draw our little table here, right, where we say each element, so our inductor and then our resistor each one needs an elemental equation or a generalized Ohm's law equation. So what is it going to be for the inductor? So remember, we're not going to write the elemental equation.
Oh, yeah.
We're going to write the generalized Ohm's law elemental equation, right? The impedance form. So it's always the same, right? It's VL equals what? IL CL. V equals IZ. It's always that. And then what is it for the resistor? Yeah. And we should say what these impedances are, where we say that ZR is the easy one, right? What's the impedance of a resistor? Just the resistance. And what is the impedance of the inductor? Yes, that is the definition of it, but we solved for an expression in terms of the inductance and J and omega.
J omega L.
J omega L. Good. So, here's the first little nuance to the steps that I will add in. I recommend not plugging in the impedance values here until the very end. Otherwise, you gotta bring all these complex numbers around with you. You don't want that. You don't need that. It's better without it. So I just leave it as ZR and ZL. Okay, step 4. Half of this is just not getting stuck in the algebra. And I'm trying to give you like guidance for how not to get stuck in it. So step 4 is KCL, right? And KCL for this, there are 2 nodes, neither of which are connected to a voltage source. So technically, our rules say we should write one for each node, but remember that these 2 nodes give the same equation, right? That all the current going in IS is equal to IR plus IL. And in fact, we're going to want to use this equation to eliminate one variable soon, right? And I want to eliminate IR. And so I'm going to write this in terms of IR equals. because I'm just skipping a step. IR equals everything going in, IS, minus everything else coming out, which is IL. So IR equals IS minus IL. Could have written it IS equals IR plus IL. Also totally fine. I'm just thinking ahead to the next step. Well, the 2 steps. Step 5 is to do the KVL, right? How many loops without current sources do we have? Just this one, right? This one's got a current source in it. So this loop tells us what about VR and VL? They're equal. So I will say VL equals VR. So 6, really, we have 4 equations and 4 unknowns. They're algebraic. Not too bad. We could do it. They're not highly coupled equations. When they all have like all of the variables in them, that's when they're highly coupled, and that's when it sucks. In this case, not too highly coupled, so pretty straightforward to solve. So what we typically do is our step A, we rewrite our L and our R, and we say, let's eliminate 2 variables. Let's eliminate IR and VL. Okay, we don't care about either of those. Well, we do care about VL, but they're like, you know, we're solving for IL first. That's what we're going to shoot for, and then later on we can solve for VL. I think that's the easier way to do it. So we're going to eliminate IR and VL, and we do that by just substituting KCL and KVL into these L and R equations. So the first one, VL is just going to be VR. So we could just say VR equals IL ZL. And we're solving for IL, so I'm going to rearrange that to be IL equals VR over ZL. The other equation is substituting in the KVL. We have VR equals, substituting in KCL this time. We have IR substituted in instead IS minus IL times ZR. Okay. So we eliminated 2 variables. Let's eliminate our remaining variable to get IL, which is the first part A was asking for what IL is. So we have, so I'll say eliminate the R, and we get that IL equals, so it's VR over ZL, so I am going to have this expression in there for VR, so I'm going to have a ZR in the numerator still, and a ZL coming in the denominator. All that is going to be multiplied by IS minus IL. And now we have only IL and IS. IS is an input, so we're good to go. We just need to solve for what IL is. So rearranging, we get, let's multiply both sides by ZL over ZR, and then move the IL term over. So that's going to be ZL over ZR times IL, and then I'll move the IL from this right-hand side to the left-hand side, and it becomes positive. This is an L. And that is equal to IS. Okay, we can factor out IL, right? this one's IL. They're both IL. So IL. So IL is equal to, we can just divide the other side by ZL over ZR plus 1 times IS. We can, I don't even know if it's really simplified, but we can sort of simplify it by multiplying by ZR over ZR, which gives us ZR divided by ZL plus ZR. IS. We might be tempted at this point to say, oh, is this like a current divider or something? It is, yes, absolutely, but I don't want us to make generalizations from this example. In the lecture I'll do on Friday, I'll explain how to do current dividers and voltage dividers with impedance. So I don't want to worry about that yet. So in a sense, we're done. We need to plug in what IS is, right? And we need to plug in what ZR is. So let's plug in what ZR and IS are, okay? So ZR is what again? R. So we have plus R down here. What is ZL again?
J omega.
J omega L. And then IS. Before we plug in IS, let's think about the form we want to plug in IS as. So it is A sine omega t. Now, if we want to write A sine omega t in phasor form, which we're going to want to do so we can combine it with what we will turn into phasor form with for the impedance. If we want to write this A sine omega t in phasor form, we can either use the so-called sine convention for the phasor form or the cosine convention. But cosine is the standard. Let's just use cosine for this problem. We'll just do cosine phasors. Even though our input is sine, we could use the sine phasor and things would actually be like a smidge easier that way. I think it might be useful to learn how to do the cosine even though we have a sine input. So something to keep in mind here is that sine omega t is equal to cosine omega t minus pi over 2, right? It's minus. The only way I know that is going back to this every damn time and drawing a sine and a cosine. Sine and cosine. And I think, oh, I want to shift the cosine to the right by pi over 2. And when you want to shift something put to the right, you got to take its argument and subtract that value. It's the only way I remember. Also, you should be able to plug in a number and have this work, right? Sine of 0 better be, so it's 0. So cosine of 0 minus pi over 2 is cosine of negative pi over 2, which is 0. So that works out at least. So we're like feeling confident in our phase shift. Okay. But unfortunately, it also would have worked if we did plus pi over 2. We couldn't check it that way. Okay. Yes. So let's do. We didn't finish this yet. So if we're gonna write our phasor in the cosine convention for a sine omega t. How are we going to do that? Is of t equals, we're going green for this equation, apparently. How do we write it in phasor form? Do we ask Google? No. No, that's not the answer. Okay. We remember our phasor form was we take something that's in the form a cosine omega t plus phi, and we write it as a e to the j phi. That was how we did it, right? I even had a diagram that looks a lot like that on the left-hand side. So you just take the a and you put it there, and you take this phase shift and you put it there. So what should I do for my IS? Sorry?
You said first.
Okay, fine. E to the negative j pi over 2.
E to the negative j pi over 2. So you use this phase, and you put it in the exponent of e next to the j. Very good. Is there anything out front?
Well, wouldn't it just be A then?
Yeah, just a. We happen to use the same a here, so. Yeah, so a e to the j minus pi over 2. Or e to the minus j pi over 2.
Would A equal 1 for this one?
A is, we're not assuming A is equal to anything specific in this. Yeah. And that's why we just left it at A. If we were assuming A was 1, we would just say e to the minus j pi over 2. Okay, so we've got our input written in phasor form, which is good, because we're going to combine it with another phasor from the impedances. So we can just go ahead and write it. And since I wrote all of that equation in that, we have to write it in green over here too, just for fun. Minus j pi over 2. Okay. So I will switch back to black now and go to the next page. So we're writing IL equals things, right? So I will write IL equals, and let's come back here and say, okay, let's write this denominator and this numerator in phasor form too, because we're multiplying and dividing things. So when you multiply and divide things, we like to be in the polar phasor form, right? So let's do that. So our numerator was r, and now it's going to be r e to the j what? 0. Because all real, and no imaginary component there. No, the phase is 0. And then we had this complex number here in rectangular form, right? Real and imaginary components. We know we can convert that using Pythagorean theorem and arctangent into a phasor form. But we're also not really feeling like writing all of that crap because it's big. So we're going to just take a little shortcut and say, whatever that magnitude comes out to be, we're going to call that M1, magnitude 1. And we're going to call whatever the phase comes out to be phi1. Just whatever the phase is. It's like arctangent of something, right? We will later specify what those are, but for now, we don't want to get sidetracked with those details. So we're going to say, oh, okay, it's whatever that is. And we're still multiplying this by a e to the negative j pi over 2. So we can combine all of the amplitudes by multiplying and dividing them, right? And we can combine all the phases by adding and subtracting them. So the multiplications all come out to be R over M1 times A, right?
Okay.
Times E to the is you've got a 0 phase to add here, so that one's not making a contribution. We're going to have this e to the j phi. The phi is in the denominator, or the e to the j phi is in the denominator, so its contribution will be a negative. So they're both going to be negative. So negative j pi over 2, or I guess I'll do phi 1 plus pi over 2. That's the order they were in. Phi 1 plus pi over 2. So they're both negative. That's why I factored that out. So, I mean, in a sense, we're done, right? We're in phasor form, but we have our new amplitude and our new phase. But we should rewrite it in trig form as well, at least just to get practice with that. So, what is this in trigonometric form? So what's the amplitude going to be? R over M1 times A. Cosine or sine? Cosine, because we chose to use, back over here, the cosine convention for our phasor, right? So we're going to go back to a cosine. Cosine, and what's inside the cosine? Right, you always have that omega t, right? That omega t stays there from, it was in the original sine input. And then what's next?
Would it be just a negative phi plus, like with it, oh yeah. I was just gonna put it in parentheses.
Yeah.
rather than-
Yeah, exactly. So you could put them in parentheses and then distribute the negative sign. Yeah. Excellent. Excellent. So, our input was in sine form. It was a sine, though, right? And not a cosine. So it's kind of nice to have the output also in sine so you can see what the phase shift is between input and output. So let's rewrite this in terms of a sine. Which is just that pi over 2 shift the other way this time. And that's our answer. But we do need to write, we kind of cheated by saying, oh, it's just M1 and Phi1. We should probably write what those are, right? So where M1 is, we define it to be, it's the magnitude of this denominator, right? So if we look at this in the complex plane, it's always useful to think about things in the complex plane. Complex plane, we have our real component is the resistance. So there's our R. And then our imaginary component is omega L. It's kind of hard to make it show up on top of this black, but like that. Imaginary is omega L. And so our oh yeah, there we go. What? I didn't mean to do that. There we go, that's what I wanted. A line. So what we want is to represent that instead of rectangular form, r omega L, we want to represent it as a magnitude m1 and a phase phi1, right? So that means that our m1 is going to just be, by Pythagorean theorem, square root of the real part squared plus the imaginary part squared. So we can write that. Square root of the real part squared, which is just a resistance, plus the imaginary part, which is omega L squared. So that's our magnitude m1, and our phase phi1 is just going to be the arctangent of the imaginary over the real, right? It's like a triangle, right? So the opposite over adjacent is our tangent. So arctangent of the imaginary, which is omega L, divided by the real, which is r. So that's our solution. We could plug those in, but it doesn't look like it's going to simplify that much. In fact, this is the same solution that we got, I think. It's a slightly different form. I didn't double check. In the last lecture, we went back and we looked at how we solved it before, what the steady state term was. And like, we have to divide through by something. I'm pretty sure we got it right. They should be the same, right? The steady state solution should be exactly the same. Maybe we might have a couple more minutes in this class to actually double check that. That would be fun. Okay, so we got IL. IL is solved. So 7. We want to find VL from, there are two ways. Actually, somebody brought up this other way. I'm going to do it. Let's do it this way. From generalized Ohm's law, so VL equals IL times ZL. So somebody else pointed out, oh, you could just take the time derivative and multiply by L. Right, that's our old elemental equation for an inductor. We have IL, so that's how we did it before. You could totally do that again, and taking the time derivative is actually trivially easy in this case, so it's kind of nice. But we're going to use this other method because it's 6 or half a dozen pretty much. So we know that VL is equal to IL times ZL. IL, we have all these different forms of IL. I'm going to recommend we use the phasor form of IL right here because we're going to combine it with ZL, which can also be represented as a phasor, and then we'll convert back to trig form. So VL is equal to R over M1 times A e to the minus J phi1 plus pi over 2 okay, so that was IL times ZL, which, let's plug in ZL. ZL is in rectangular form, which we wrote back here, was just J omega L. We wrote that in phasor form. It's omega L e to the J what? Pi over 2, right? That one's just pointed vertically, so phase is 90 degrees. So we can write this as being omega L e to the J pi over 2. And combining them, we get R L omega divided by M1 times A and E to the, what's left over when you add these together?
J phi1.
Yeah, the negative j phi 1, but yeah. Because the pi over 2's cancel, right? Negative j pi over 2, positive j pi over 2. Add the exponents, and they go away. Conveniently. Sweet. So, we have our phasor representation. Let's also write it in a trigonometric representation. And we have a cosine omega t minus phi 1. Now, that's great, but once again, we had a sine input, so we should probably change that into a sine RL omega m1 a sine omega t minus phi 1 plus pi over 2. So that's our phase shift for the sinusoid. Okay. We have 3 minutes left. First off, before I verify that the other problem got the same answer, I'll answer questions if you guys have them about the process, 'cause that's more important. So, do you guys have any questions about this? I think that this method is conceptually a little bit easier to work with. Well, I don't know. Conceptually, they're about the same, I guess. But I think most of the time people just get a little bit bogged down in the phasors, polar versus rectangular and all that, cosine versus sine. Try not to get too bogged down in it. That's part of why I recommend getting all the way to this step before plugging anything in. If you get to that step and that's right, like for instance on an exam, and then you somehow botch the complex algebra, like, man, that's not a big deal. I will deduct some points because you do need to know how to do that. But at least conceptually you have it and you can just march forward from there. It's nice because you didn't have to come up to step 6 and then have to deal with differential equations. You can solve it all completely in the way that you've always known how to solve linear algebraic equations, and then and only then do you need to worry about the complex stuff. So, all right. We don't really have any time to do it, but anyways, if we go back and look at the solution we came up with for the last example, it was exactly like this, except it had a plus e to the minus something t term. And that term is the transient response. So we only ended up with the steady state response. But that's okay, that's all we were looking for. Okay, so yeah, transformer problem, not until next week. Or maybe 2 weeks. I gotta look at the homework. But in any case, no transformer problem this week. And the problem that you're doing right now, next week you're going to do again, but with impedance methods. And especially in this problem's case, the differential equation is actually quite a bit of work. Impedance method for that problem, special problem 1 in this week's homework, is going to be so much easier next week. So, yeah, that's part of it, is just like getting you to appreciate the impedance method. So, enjoy, and good luck on your homework.
Can I avoid trig functions at all costs?
Yeah, that's fine, but if I ask for it in terms of trig, you got to be able to convert it to trig.
Where
Yeah.
was your lecture?